their own with their analysis. Like Walden-Zupas is a good reference too for how to handle definitions of charges. Great.
Yeah, it's just the inverse square law, or the inverse of force, just kind of turned into uh, having your mathematical equations equal zero. It looks like from Noether, and Einstein was able to recognize. I think it's called, what was she calling it? The duality. I can't remember what she was calling the duality. Uh, and Einstein was able to recognize that and saw that it was true, and just was able to say, yeah, that there really is a quantum mechanic that gives justification to the fact that there is something that is uncertain, and whether or not that was missed or recognized, it just seems like it was used for the wrong reasons, uh, just to envelop this actual story of quantum mechanics, which wasn't really ever justified. Again, because string theory could have just been coherence and the first dimension uh, going into a second dimension, but never actually being quantized by uh, second dimension accurately. So
of this soft factors.
And they use epsilon, which is just polarization. And then and they can use h, lowercase h, or uppercase h. That is usually their wave. Their their j can be equivalent to joules, which will equal just that metabolism effect. The effect of, it's just a metabolism effect, meaning it's not quite entropy, meaning like the degradation of uh, radioactive decay in the universe, but it's an actual metabolism effect in, might be cosmic inflation. So they also use sigma. Sigma, I want to say, usually represents their frequency, but they can also exchange their S for their sigma, and their S can equal frequency. But usually their sigma is equal to the orbital. So if they're talking about an orbital, yeah, I guess they can be talking about a classical or a mechanical angular momentum, and then S will become frequency, meaning it's like a portion of the wave. And then this is always I think these are their factorials, where because they'd have to, it seems like they have to have their brainstorming for how they're going to uh, translate the phenomenon, and they have all of their factorials first, or their calculus first, and then they get into like their algebraic equations. I'm not sure if that's exactly how it works, but yeah.
And free factor. It's gonna be great.
And then a free factor. I mean, of course, they always have, like, yeah, this can go both ways. Something's free in the problem, and that just means that it's interchangeable, because they know that quantitatively they can't have anything that is absolute, and they know that they have to know that their problems are interchangeable. Like their if they have like an A to Z problem, that typically means alpha, omega,
So
and
now we get to play around with memory
start and
types
beginning, and I mean,
just kind of seeing what these self-vectors actually are and where these word identities are coming from. So,
and they also have like Ward invariants and Ward invariants, and like that would just be uh, just different places where there is a control. Like a Ward invariant, I want to say would be like a Noether, an Emmy-Noether equation where they have, again, something that is going to be like interchangeable in the universe. But if they had like the opposite of a Ward variant or a Ward invariant, like a Ward invariant classifies anywhere, any situation going on in space or in reality, because you can move it around, you can move the point wherever you want to go, and since it's it's an invariable, it's never stable. That just means that they have an equation for something that it's usually going to come down to that that epsilon, which is you know their polarization. So they really are just trying to figure out, like, they're just quantizing. I don't want to say kinetic energy because they're not doing kinetic energy at all, but they are doing extreme, like, theorems, formulas, and theories and everything, probably from Einstein, that are getting them back into classical mechanics. Because if they don't travel back to classical mechanics, like, they have to come back to like a zero or a non-zero, and so if they quantify something as a non-zero, then that means they've calculated certain situations. They've calculated certain energy in time. But if they come to a zero, that means that they've calculated something perfectly, I would say. Meaning they've calculated the classical mechanics of something, because they've realized the force. I want to say it's closer to that, but yeah, I don't want to totally butcher this.
it's actually good at this point to imagine massive scatterers just for the moment, because when we look at the self-vectors for them, you can see some more kind of like classical electrodynamics results in intuition. So right now I'm going to write gamma, what I mean by this is a Lorentz boost factor corresponding to the velocity of the guy. So this is slightly different notation than above, but it's kind of clearly write gamma sub beta to keep that into account. So this is how you write the momentum massacre. So now we're basically going to plug into the soft vector this for momentum for like a single charge. So this soft vector is a sum over the external photons, say, attaching to different legs, and this is just looking at the contribution from one of those legs. So just say plug in a single one. And essentially from this equation, we can get what we expect for a relation. For the massive guys, none of the charges are going to leave through null infinity. So along null infinity, you basically have a relation between the radioelectric charge and the radial field from the electric charge, however it's moving, and the radiative field that happened. So let's write this down. Yes.
So I'm trying to figure out the electric field and the radioactive charge or non-charge displacement charge, and then just coming up with a toroidal, or that hyperboloid, and it seems like that's where, in the direction where it would go. Because if they figure out that, well, if they figure the black hole is a sphere, then yeah, they have to turn it into something else. Or if they do it in a two-dimensional, if they do the galaxy in a two-dimensional plane, they have to figure out, well, how is it a sphere? And then they have to figure out, well, how is it a toroidal or a hyperboloid? And it just seems inconclusive in that sense, in the sense that, like, they are projecting. They're projecting their problems onto the universe. They don't have like an unequivocal truth for. They don't have an unequivocal truth for certain matter.
Expression like this, like delta AZ, would be equal.
I mean, it would all come down to that they're calling the black hole matter. Like the black hole doesn't have any force; it has matter. Therefore, it has to have some type of quality that keeps the galaxy. Because I mean, people can see the galaxy, with their naked eye, and it's just like that really wide streak of stars uh, at night. Like in a desert or something, and it's just like a huge. It's just like all the stardust, and it's just like clumps and clumps, and so spinning on our axis, if we're at night, that means. So I mean, I'd almost say that it's like southeast, because I mean, if we're at night, well, I should say if the northern hemisphere is at night, well, yeah, I can't really do all that. I mean, I can't say. I mean, obviously they'd be able to figure out like from the axis, the rotation of the Earth, and the revolutions around the sun, uh, and determine where the two-dimensional plane um, of the galaxy would be, because that galaxy is something really far out. And then once you, because sometimes you can't even, I mean, sometimes you can't even see the galaxy with your naked eye, like because there's too many stars or something. I don't know. I mean, it really doesn't make sense to me. But I mean, it's just the fact that trying to figure out the two-dimensional plane of the black hole, and then once they have that, it's like they have to move on. Like they have to use other mathematics to figure out, well, like to test even. Does it have centrifugal force? Is it really, pulling us in, or is it pushing us out?
Equal to e over 4 pi. So this expression right here is a statement that just from the mode expansion that I have. So I've plugged in what A is, and I've looked at it's the step that it takes. So basically this is looking at some integral of du of A, giving the delta. And this is just the soft factor times the factor of omega pulled.
I mean, even if she says du, it could be like as in the delta. See, they use a lot of terminology, but I mean, the delta, the lambda, all these different, they just have all these different correlations with what is it called? The double split experiment, like how they can have a frequency or a wavelength and properties like that. Because it seems like they're important to figure out like the two-dimensional classical, or even because if they have a quantum idea, then they can turn that into a classical thing, whatever. I should stop talking.
Pulled down from the derivative. So this is just from the mode expansion. Right. And now, what's kind of fun is if we take...
I didn't understand why soft factor appears in the mode expansion.
Because this is like when I wrote down the mode expansion before, and we had that like A sub z is equal to some prefactor coming from there. And then A plus say minus of omega q. Like that. Right. So I've plugged in this expression into here. And then, because I'm evaluating delta A, which is the integral of this guy over here, so I integrate it to du, then I'm basically going to pick out du of this guy is going to pull down a factor of omega. And then the integral is going to basically have support, like a delta function support at omega goes to 0. And so there's some subtleties of like which order of limits you choose, in the sense of like you regulate it by like writing like some e to the I omega u du, like as this omega goes to 0 to pick out omega q, omega, or something like that type of thing. But otherwise, essentially it would make sense that the long time interval is going to pick out the zero frequency part of the creation operator. So if we now literally interpret that as you take the limit after, so like you evaluate this and limit as omega goes to 0. That's
all that goes for a single photon, and soft factor is more complicated logic, right?
So
single photon attached to other stuff.
So that's the key thing. So this is like a single photon, and the soft factor is going to be sourced by each of the lines of the scatters. So we have some, in this case, massive charges, say, and then we have a photon coming out of it. And so the soft factor here is the sum over all of those guys. And so in a sense, this is now inserted in the scattering process. So the scattering process, when A hits each of the external lines, is exactly what is going to end up. Right, so we have this picture of, in the Feynman diagram, you have like something scattering process happening, and then you have the soft guy attaching to each of the legs. Right, so I'm drawing different possibilities, and then like you had some of this one with that one, and so essentially that's the different sums in terms of the soft factor. And what I'm saying now is I'm just going to look at the electric field configuration for a single charge that's boosted. So they have a set of momenta, and I'm just going to plug in a single component of this guy, which is the sum over that. And so if I do that, which is kind of fun.
Yeah, so I mean, just these soft factors. Oh yeah, soft factors. Was that the word she was using? No, I think yeah, by soft factors, I mean I just think that they have I should say she. She. Well, I kind of got lost in there, but yeah, trying to figure out not the toroidal, but the spin. Um, they're trying to understand this, like, well, I guess that P equals M something something. That's the spin effect, and then something in her little diamond or square uh, with like a frequency in it. That would be they would have like the determination for their superposition, and it's like their lens and their angle and which part of the sky they're looking at, and determining this if they can determine the spin, then they can determine how the galaxy is changing over time and what the exact truth of the black hole would actually be. I don't think it's completely illogical that we live in like a stable like in a stable actual galaxy, and when they're looking at other galaxies, they're not just looking at galaxies or stars um, in our own galaxy, but it does become very confusing, I would say. And I forgot what else she was talking about. I don't want to always speak. I don't want to always cut her off. But you heard her say, frequency equal to 0, finding out superposition. I mean, a superposition for them is
So I'm going to do this.
the problem.
I'm getting up, which is very nice to see.
And she said B was a delta, so your delta could mean any connotations of the double slit experiment, I would say.
I've taken the soft factor, which is the sum over, so that's minus the sum over the electric charge times P dot epsilon over P dot Q. And I looked at the particular, so this is M over PKs, I looked at the particular contribution just from P. So
again, now she's calling the sigma the charge. Again, so a lot of this stuff is interchangeable. There are a lot of there'll be original theorems or formulas, and she can plug them in, but so she has a charge, a particle bit, a frequency, and she'll work with those three things. I mean, she can have energy squared. I mean, they can square energy all the time, because then they just have to do this sort of division thing, and they split their formulas in half or something, and they have they can quantify half the energy, and then they can work with that energy, and then they can have like their Cauchy slice. I mean, it's incredible, but it's not explained well, I don't think. I mean, there are descriptions on Google Images that explain some of these equations, which is cool, but yeah.
I don't worry about the sum, I just have a single particle, and I plug in the soft factor and act with this differential operator on it. Then I pick out just this guy. And this guy should look familiar for just looking at a boosted charge electric field. So basically what I'm saying in the following is that this is one of our strict component of just the radioelectric field for a charge that's boosted.
Right. So they would look at, I mean, they look under the microscope. They look under the microscope to see out of the telescope. They don't look out of the telescope to see into the microscope. They definitely, go to CERN to quantize what they see at the Hubble or the Webb or at LIGO and CERN, respectively. Like they look under the microscope to be able to see out of the telescope. And it's not so much a problem than it is just very unexplained. And it's maybe, I don't know, like I just don't see, if people really knew what was going on with physics, they'd just be kind of like dumbfounded by, why are you guys doing that again? So yeah, it is very interesting and all that stuff. But it's reached its peak, it seems like, and so again, I don't really know why. Oh, because she was mentioning charge, so they can have a variant. Like if they have invariants or they call them Ward invariants, that means that they're interchangeable. Okay, so she can have a charge effect on a certain superposition in space seen out of the Hubble telescope, trying to figure out what the black hole is doing, and then they can say, and then they can, they can quantize the charge by information that they would have gotten from CERN. Like they could have, oh well, if these distributions of stars out in space are having this effect, then let's go back to the information we got at CERN to see what the photons are doing when we can simulate this effect. To some extent, I feel like that's what's going on.
With this velocity and you're in this direction, you're looking at it. So, upside of this is basically soft vectors are just, in some sense, like these memory effects are telling you just this is the final state of, say, a charge. And so you can then interpret this equation as saying you have, in this case, the radioelectric field changes because you have some in particles and some out particles. And the amount of radiation that you observe is just corresponding to the change that happens. So in some sense, what I want to say is that when you have these memory effects, there's a kind of final state and initial state that you specify by having the scattering process. And that will constrain some amount of radiation that you observe just because of the fact that you have this net change in the field. So you have this guy for this, and you can do the same thing for the massive case. When you're looking at some bonding mass term, then essentially the expression that delta MB.
Like they're saying, they can determine radiation under a microscope and then look through the telescope, and if they see certain activity, or I should say, activity, is it activity? Certain dormancy, like in the universe, and determine whether or not that dormancy is changing through, radiation that they would understand better through the microscope. Then this can determine what other bodies are doing in space, and it's a lot.
This is that expression from the constraint equation, and then what you end up getting out of it
Again, that expression could be her invariant, unstable, changeable charge. She's calling it du, Well, I mean, if I mean, she was calling it. I don't know what the U is. I know U. I know J is joules, and she has C squared there. So wave alpha. It's a lot of stuff. I mean, I think she has. Does she have 0 squared? Oh, it's D squared. Yeah, D squared. Yeah, I don't know. I used to think that U was universe, or U was up. Oh, it's U is upsilon. U is upsilon, and that means I can't really remember what upsilon means. It means like their point of view. Like again, I think if she has delta upsilon, I think that means like point of view of the wave, something like that.
It's just literally evaluating Weinberg's soft vector.
And if she has a wave, that means she has a two-dimensional plane of the matter that she is playing with. Well, and also the space, or I should say the red shift and the blue shift that she is playing with. She has they have a constant for that, and then they go to a different problem using those properties of their original constant or something. So.
For single particle contribution.
I'm just kind of confused now why this is memory effects. Well, it's memory effects because, yeah, they are doing the singularity thing. So this is like they're doing the singularity from space, and that seems just hugely manipulated for me to be able to think that's right. Like, how are you going to determine that there was ever a singularity or was ever a Big Bang, and you just have the farthest point in space that you can reach with your telescope, and you determine that as your Big Bang, and then you determine you can't see anything past it. Like, so what? I mean, it just seems like, well, if you had a bigger telescope, you would be able to. But anyway, and then you measure all of that radiation. That's what they call it, right? Radiation or radioactive decay, or all that anthropic or centropic force that was distributed. It's a mindful.
So basically what I'm just saying is that the soft factor is again just telling you what the expression is for boosted mass. Or it's basically...
Is this interpretation important for the later? Or it is?
Because kind of it's a cute result. But the fun thing about it is the reason...
Yeah, I mean, it's equivalent to the light or the energy in the universe. I mean, it'll ever only, only ever equal energy or the light, I should say, because everybody thinks energy is light. And everybody thinks that the speed of light is everything in the universe. Well, that makes sense if you consider everything to be made out of photonic particles, but in reality, that's not the case. That's definitely a quantized way of looking at things. So, I mean, you're talking about red light and blue light here in outer space. It's just, oh man, I think I'm getting burned out myself. I don't know where she finished on. I mean, I've watched 7 minutes of this.
The reason why it's important is what I'm saying is the following, is that you can see that this is just a contribution from a single soft particle. So what we're looking at in this case is the radiation that comes out. And the radiation is going to be related to basically the fact that there's a change. So you've set, this is the initial, and then there's a final for it. And when you have incoming particles and outgoing particles, there's a certain amount of radiation that also comes with it, no matter how you get to that point, in a sense. So that's what I'm saying. The origin of memory effect is because of the fact that you have this.
She's thinking the memory effect from singularity of the universe, from the Big Bang of the universe. I mean, this video was made 5 years ago, but from the Big Bang, the memory effect of that, and determining and doing the calculations on determining the positions of the bodies of redshift in the universe, from that single position, from the furthest body that they can understand in space, and then calculating, doing the calculations for, memory. Their memory effects would be, well, how old they are in space in their terms, like from the Big Bang, which I don't know, which doesn't make sense, I guess. And it doesn't make it definitely doesn't make sense in general relativity. It makes sense in special relativity, but it's not explained that way. It's explained like that's the general constellation of our universe, or consummation, like that's the general genesis and birth of our universe. So it's explained as if it is real, but they know it's all special relativity, so it's not real, but they explain it anyway like it is, as if people should know that. And well, and then they always have like this chaotic, like, I don't know disposition. Like, I don't know is the most important word in a physicist's vocabulary. It's it's important to not know. I mean, that's a load of shit.
Like radiation is conditioned by the constraint equations on the initial and the final thing.
Yeah, again, a restrained equation. I mean, it's just not right to tell people you have the answer and they already don't know. It's not right to tell people you have the answer on the premise of people don't know what the fuck you're talking about. So yeah, this will probably get buried, but yeah, it's just that's just the reality of what's happening. 90% of the planet might not even care whether or not the Big Bang is real, but out of that 10% of people, 99% of those people will think exactly what these people have said it is. And it's just complete bullshit because they could never know. And these people could have just been saying the Big Bang we're talking special relativity here. We're not talking general relativity. You can't figure out anything in general relativity. You can't quantize a single one of their theories in general relativity because nothing in the universe is really making sense. Once the door is closed on physics and you understand, well, there's force or matter or bits and particles, it doesn't make a difference. You can still talk about those things, but you're never going to have an exact answer. So it's not to say that these people are wrong. It's just to say that it's a contrivance to say that they have the answer because they don't have the fucking answer. There's no fucking way these people have the answer and that we're in a vacuum right now. And that Einstein or Newton or Galileo ever thought we were in a fucking vacuum. It's like saying we evolved. It's like saying Charles Darwin said that we evolved from the primordial ooze. Charles Darwin never said we evolved from the primordial ooze. I mean, there was obviously so much to the story of evolution, and there should be so much story to the story of physics, but physics hasn't become that. Physics has become an answer, and that's the wrong way people should view physics, in my opinion.
So this is just showing that it's coming from boosted charge, and you can see, like, oh look, I have some set of charges that started this way and they end this way, and then I see the radiation from it, and so it kind of simplifies like what the origins of the things are because you kind of like this is like what you've seen before, so it's like, yeah, I know. No?
Do people understand this?
Oh, no. No? Come on.
Sorry.
No.
Let me explain it.
Okay. Do you understand this expression, hopefully? Or this expression? We got this one?
Yeah, this is a simple expression.
Exactly.
But all the steps
This is another point, is getting it to a simple expression. So, okay. We have an end state, and it's specified by some momentum, some velocities, and some charges, say. And basically these memory effects are corresponding to super translations, super rotations, and the OLRG one.
The Olargy. Yeah, super translation, super what? Everything is just super, man.
So, in the sense that if you just looked at a charge and you looked, it's boosted some velocity. So P and Q are telling you Q.
Again, they're talking about this boosting shit. This is not what their theory is. Their theory is only boosted. Their theory only has time as an object in singularity. That's how I'm going to end this video. They don't have they don't have time in classical spin mechanics. They only have time as in a vacuum in quantum spin mechanics. There is no there so and then so because they're talking about boosting charge, they're boosting all this charge and trying to quantize light years, in my opinion. And they're doing a complete just it's just a what is it like a I don't know. It's just disingenuous to say that there's these light years are real because you're saying that the telescope is traveling through space. Like your view of the telescope is traveling through space. Therefore, I mean, all it's doing is going. I mean, that's what the Hubble telescope or the Webb telescope is doing in space. That's all it is doing is changing its direction. See, they're not talking about general relativity. They're talking about this bullshit special relativity, and they're not saying that. And they're saying that there is an epsilon, meaning like there is this distribution of charge, not the epsilon, but the upsilon is like maybe their little cheat code to be able to say, well, this is, this is giving time a dimension. Well, there shouldn't be a dimension of time in outer space in general. Okay, there should be a mechanic. Yeah, sure, we can have a dimension of time on Earth. Like we can say, oh well, it's 2:30 p.m. or whatever, but that's still not even a dimension. That's just a calculation, a very good calculated piece of technology and theory. That's what time is. But time can never be relative to viewing objects traveling at a different distance in time. Because she's going to be talking about this coherence thing, Einstein's coherence, and that's not how it should be viewed. And I think people are getting that, and I think people understood that they wasted their time, and they're really just using the optics of CERN and atomic colliding and atomic splitting and all of this stuff. It's just refraction and diffraction of photons, but they're trying to learn the qualities of how those particles enter and exit through their lens. But then to have these time effects, like these lapses, saying that they have these like lapses in stationary space, like in stationary space time. Like that is completely ridiculous. It's just because they're working with specific calculations, working from the furthest point in space. The furthest point in space is allowing them to have a entropy. It's allowing them to have a cosmic background radiation that they can't see, that is pushing the universe in some direction. And when they give that, Einstein didn't even believe in black holes. And they're saying that wormholes and vacuums and all this shit is it's bullshit. So, let's see what else she has to say, but I'm about done.
And the direction that it's going. So this would be its radioelectric field if it were just moving with nothing happening. So in a sense, what happens is in the soft vector, you have a sum over in minus out, or out minus in, depending on your choice of sign convention. And what you're doing is you're taking basically.
Again, if you have a calculation, you have particles going in, you have particles going out. Okay? Yeah, you have a lens. All right? You have like you have a screen or whatever. Yeah, you have a certain two-dimensional theory that things can't escape, and things can escape. That doesn't mean it has any real theoretical value. It doesn't give any indistinguishable evidence that you guys got to the edge of the universe. That is complete bullshit. It's like that. They got to the edge of the universe with their telescope. Okay, like we live in flat universe. We live in a flat singularity, a flat vacuum, and they know this stuff is crap. But they're teaching this stuff, or they're reciting it, or I should say, they're renunciating it. Oh my gosh.
Basically looking at the fact that there is some radiation that you observe because of the difference in these final states. And so all I'm saying is that the soft vector, which is a measure of the radiation, like this extra soft particle, say you're looking at the gauge field, that's the 1 over like the A sub z component, is just telling you from the soft vector that you have some net change in the distribution of charges due to the in and out state. So
yeah, that's all it is. Net changes. I mean, she's so smart, but it's just not being explained. I mean, it's being explained to really smart people. And they seem to get it too, which is the incredibly sad part. It just seems to be like their own little fun club, but yeah. Yeah, you're just explaining the distribution of charges, like in a picture, in a photograph of infrared with red shift and blue shift, and you're saying that's the Big Bang. Yeah, well, I'm sorry, it's not. A Big Bang is a Big Bang is causing kids right now, and has caused many kids and many animals to be born. Big bangs are happening all the time, and they're causing death. There's no such thing as a fucking Big Bang anywhere else in the entire fucking universe other than fucking Earth.